bicycle, bicycle, bicycle. I want to ride my bicycle, bicycle, bicycle. I want to ride my bicycle. I want to ride my bike. I want to ride my bicycle. I want to ride it where I like.
Good morning, good afternoon, good evening, whatever the case may be. We are back and better than ever. I just could not stop. Bicycle by Queen. Prior to that point, it just would have been rude. We are talking about variance and standard deviation with probabilities because we've already talked about variance and standard deviation. Should be pretty short. Let's get to it. All right, so from the expectation lesson, we're going to consider again 10 counters here. And this is just kind of deriving our formulas that we're going to use. Where we have, let's see, we have a 1 counter that shows a 1, 4 that show a 2, 3 that show a 3, and 2 that show a 4. Okay, and we've already seen that the expected outcome is equal to the sum of each of the events times its probability, which makes sense. And so, therefore, the variance of this is the standard deviation squared. So we're just going to throw in the frequency. We're going to multiply the frequency by our variance formula that we already know and apply it here, and you can see that it becomes the sum of each random variable minus the mean, the quantity squared multiplied by p sub I. And if we consider a general case, and I'm not going to go through all of this, we get to the variance being equal to the same thing, the sum of x sub I minus mu, the quantity squared times the probability. And so we get these nice little formulas in the book here that we are going to use that all stem from this and from what we've learned prior. And it looks a little bit different on our formula sheet, but it's really the same thing. So let's apply it. Let's find the standard deviation for this distribution. We have a 23% chance of getting a 1, 38% of a 2, and so on. I'm not going to read the whole thing. Okay. So we are going to need the mean, of course, because we're going to be using this guy to find the standard deviation. We're going to take the square root of that, of course. This is the same thing. By the way, this is the same thing as the probability of x sub I. This is just that the probability that the random variable x is equal to that specific value. Okay, so we already know that the mean mu is equal to the sum of x sub I times the probability of each particular event, or each random variable, I should say. So that's 1 times 0.23, 2 plus 2 times 0.38, blah, 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 blah. And without boring you, we'll tell you that that's 2.39, which was also part of the lesson. So now our standard deviation, as advertised, is going to be equal to the square root of all this fun stuff. So that's the square root of x sub I minus mu squared times p sub I. I don't like writing probability of x equals x, so I write p sub I. So what would that equal? Okay, well, no big whoop, I hope. So big, long, giant square root here. So that would be 1 minus the mean, 2.39 squared, times its probability, so times 0.23, plus 2, I have to write a little smaller, minus 2.39 squared times its probability, which is 0.38, okay, plus, oh, I'm going to have to make this like a bigger house here. Okay, plus, and we just go all the way to the end, right? So, you know, we do the, I'm not going to write all of this out because I'm lazy. So that would be 5 minus 2.39, the quantity squared, times its probability, which is 0.05. And we crank all that, and we get, rounded to 3 sig figs, 1.12. Okay, so there you go. I do want to show you, because it's kind of weird how we have this formula and how it turns in to this formula here. If you look in the text, where did that go? Oh yeah, here's an alternative formula. If you're confused by that, this lays it out nicely for you. I just really wanted to show you the example. But you can look at this here, and like I said, it lays it out quite nicely for you. All right, I said it would be short. It is, so let's get right back. See how Queen is doing riding their bicycle, and that will be it. We are